Hi, and welcome to this introduction to vibrations. According to Wikipedia, vibration refers to mechanical oscillations about an equilibrium point. The oscillations may be periodic, such as the motion of a pendulum, or random, such as the movement of a tire on a gravel road. So this is the oscillations of a pendulum around an equilibrium point, and this is the oscillation of a mass on a spring. The vibrations are around us. Think about vibrator in your cell phone, the vibrations produced by tools, the vibrations produced by rotating machines such as a washing machine. Sound, also when it is produced by a loudspeaker, originates from the vibration of a mechanical membrane. An electric shaver is vibrating when you are shaving, and trams driving down the road produce also vibrations in their environment. But what is the fundamental mechanism of vibration? Well, it is based on a transfer between kinetic energy and potential energy. And in this mass spring example, you see in the middle the mass that is at the rest position, and so the potential energy is zero because the spring is not stretched. Now, when it's vibrating, whenever it comes back to this rest position, it has a maximum velocity, so the kinetic energy is maximum. At both the bottom and top positions, this is when the potential energy is maximum because the spring is fully compressed or stretched, and the velocity is zero because it's changing direction, so that the kinetic energy is zero. The same holds for the example of the pendulum. So when the pendulum is in the middle position, you see that the potential energy is zero. This is the reference height. And the kinetic energy is maximum because this is where the velocity is maximum. And at the two ends, the height is maximum, so that the potential energy is maximum. And the velocity is zero because it's changing direction, so that the kinetic energy is equal to zero. So when an object is vibrating, there is a continuous exchange between kinetic and potential energy. Now let's have a look at some examples of civil engineering structures where vibration problems can be important. Traditionally, vibrations have not been a very big concern in civil engineering, except for very high levels of vibration due, for example, to earthquakes. But things are changing, and this is because vibration sources are increasing in our modern world. Also, comfort demands are increasing. Health issues are appearing. For example, people that are subjected to repeated vibrations due to the use of tools, it's important to protect them from these vibrations, not to deteriorate their health. In some cases, also in buildings, you have high precision technologies which require very low vibration levels in order to be able to be used. Another problem is that new designs make some structure more susceptible to vibrations. And I want to illustrate that with this example. If you look here on the left, you have a picture of an old art bridge, which is a pretty massive structure and will not be subjected to a lot of vibrations. On the other hand, more modern structures, such as the Millau Viaduct, are much more slender, and in this case, they will be much more subject to vibration problems. And this trend is visible in other areas, such as automotive and aerospace, where the reduction of weight for optimal use of materials results in higher levels of vibrations. So let's illustrate vibration problems in civil engineering with a few examples. The first one is the Millennium Bridge in London. This is a pedestrian bridge that crosses the Thames and leads to the Tate Modern Museum of Art. So we're going now to watch a video of what happened on the opening day of the pedestrian bridge.
The bridge opened on the 10th of June 2000, attracting thousands of people and the media. But as the people poured over the bridge, it was clear something was wrong. The bridge was wobbling from side to side.
I got a phone call midday saying we had a problem. And my first reaction was same as everybody else's. Well, all bridges move a little bit. There's an exaggeration going on. But Roger said, no, this is real. And so I came down early afternoon, and you saw it, and you think this isn't real. This can't be happening.
It was very disappointing. We were witnessing the bridge performing in a way that we hadn't anticipated. We'd done lots of work to try and understand its behaviour. We felt that we understood it very well, and here it is doing something completely unexpected.
The engineers had tested every element of the bridge, from the cables and bolts to how the bridge would behave. Regulations and codes of practice give engineers basic design guidelines. These codes are based on years of experience and look at how different vibrations can affect a bridge. In 1941, the effect of wind-induced vibrations was fully understood after the Tacoma Narrows Bridge in America collapsed under a strong, persistent wind. But it's not just the elements. Soldiers marching can create sufficient vertical vibration to bring a bridge down. Before crossing, they're always ordered to break step.
Right step!
Signs on some bridges still bear witness to this danger. As engineering advances, the bridge building codes are continually updated. Arup researched beyond the requirements of the codes, studying pedestrian vibrations in detail.
With regard to pedestrians, we did a lot of work on vertical vibration. That is, as a pedestrian walks over the bridge or a group of pedestrians, what kind of force, repetitive force, do they put into the bridge?
Arup's calculations followed the codes in assuming that people walked randomly, and the major force they generated was vertical. But on the Millennium Bridge, something unexpected happened. People changed the way they walked in reaction to the movement of the bridge. To balance themselves, pedestrians spread their feet apart, creating a significant lateral, not vertical force. More importantly, the people's reaction was almost identical. Everyone stepped the same way at the same time, creating a synchronized rather than random force. The frequency of this force matched the natural frequency of the bridge.
The motion of the crowd was synchronized with the motion of the bridge. That's actually proved to be a very important observation. We also observed a quite bizarre behavior, that we could control the level of vibration by limiting the number of people. But it was far from a linear relationship. We noticed that it was almost an on and off situation, that either, the center span particularly, either it was vibrating or it was fine.
The vibration developed when a large number of people picked up the slight movement all lightweight bridges exhibit and locked into it.
Lock-in is the term that we've used to describe the fact that people, as they walk over this moving surface, sense that movement and adjust their gait to take account of it, to stay up, to keep their balance.
Lock-in seemed to be a problem no one had come across before. But Arup then identified two bridges that appeared to have a similar problem. One in Japan and one in France. However, reports of the problems on the Solferino Bridge in Paris were confused, and they did not identify the cause. In Japan, engineers did publish their understanding of the phenomenon, but in a journal of seismic engineering, unlikely to be read by bridge engineers.
The body of knowledge hadn't disseminated beyond those people. And Arabs didn't know about it, I didn't know about it, and specialist checking engineers, who are the most likely people to have known about it, didn't know about it.
As news of the bridge spread, Arup received reports of other bridges of all shapes and sizes that had wobbled. This meant that any bridge with a low natural frequency, carrying large numbers of people, could begin to sway. Clearly, the phenomenon was not caused by the Millennium Bridge's innovative design.
We just saw how pedestrian can induce excessive vibrations of a footbridge. Other elements like wind and rain can induce also vibrations, and this is the example of a cable-stayed bridge where the cables undergo excessive vibrations due to wind and rain. Another common problem is the vibrations of high-rise buildings, and vibrations can be excessive at the top of the building, also due to the action of wind. So you see here on the right that when you have high winds, you can have quite high motion at the top of the building, making this frame vibrate, or this lamp also vibrate. And this is the movie of a building under strong winds, and you see clearly here the motion of the building that is excited by the wind. Now I'm coming to a last example, which is the very infamous Tacoma Bridge collapse in 1940 in USA. And this video is going to explain the problem of this bridge and what happened in 1940.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
This last and quite dramatic example really shows how important it is for an engineer to understand the effect of vibrations in structures. And this is not only true for civil engineers, but also for mechanical engineers. So let's have a look at a few examples in that field. In mechanical engineering, we have the same kind of problems as in civil engineering. So vibration sources are increasing, comfort demands are increasing, health issues are appearing, and high precision technology require very low vibration levels. So new designs also in this field make some structure more susceptible to vibrations. And let's take the example of an old and quite heavy car. You see that new designs of car are much more lightweight with optimal use of materials, and this results also in higher levels of vibration, such as in civil engineering. Now, a typical example of problem of vibration is flutter. Flutter is a phenomenon that occurs due to the interaction between the airflow and the aircraft, and this movie illustrates what kind of effect it can have. So you see clearly in this movie, if you look at the tail of the aircraft, and we will zoom on it, that there is some vibration that is only due to the interaction between the aircraft and the airflow. Another problem that is very common is problems of vibrations in cars, and this movie illustrates this kind of problem that can happen.
Oh yeah, so check it out now. Okay, that's acceleration. You can see the thing vibrating here and the camera. Okay, watch, it's terrible. I hope you can see that in the camera.
Another problem is illustrated here, which can even lead to failure. So here the vibration is due to moving and rotating parts in an helicopter, and you will see how this can lead to the failure of the helicopter. We have seen in these examples that there are different sources of vibration, such as pedestrians walking on a bridge or wind blowing on a structure. These sources can have positive or negative effects on structures. Let's have a closer look at that. So vibration is due to some source, and these sources can be divided into external sources and internal sources. For example, in civil engineering, external sources are seismic activity, traffic, construction equipment, wind and waves, or pedestrians. In mechanical engineering, typical external sources are interaction with the road or track for a car, aerodynamic loading for cars and aircrafts, environment, so building in which the object is at the moment, and acoustic perturbation, which is an excitation due to acoustic waves. But the objects also have internal sources of vibrations. In the case of buildings in civil engineering, you can have ventilation systems, elevators, fluid pumping equipment, all kinds of machines and generators, and aerobics or exercise rooms, so basically human activity. In mechanical engineering, you have often an engine or a pump or a generator or an actuator or several actuators, and you can have several rotating unbalanced elements such as wheels. Now these vibration sources create mostly undesirable effects of vibrations. We can have fatigue problems, which is the fact that mechanical properties of structures deteriorate with time when they are exposed to high levels of vibrations. There are noise issues, comfort issues, health issues, and also performance for high precision equipment. And in the end, we saw that vibrations can also lead to collapse, such as in the case of the Tacoma Narrows Bridge in the United States. But we should not forget that vibrations also can have positive effects. For example, in Formula One, we use the high frequency vibrations to decrease the friction in engines and increase their performance. An electric toothbrush or a sander is also an example of positive and useful effects of vibrations. All musical instruments, such as a guitar, produce sound, which is nice to the ear. A loudspeaker is also an example of positive effects of vibrations, and vibrating seats are nice when you want to get some kind of massage. So as engineers or future engineers, we really need to understand what are the effects of vibrations on structures in order to do a proper design. This will be illustrated throughout these videos with practical case studies. So we are dealing with vibrations as engineers. And to study these vibrations in objects, structures, and systems, we need a four-step procedure. The first step is to identify the source and the type of excitation. The second one is to model the effects of vibration, so to predict these levels. The third one is to modify our design if we cannot reach the desirable vibration levels. And if this is still not sufficient, then you can use remedial measures to reach your design goals. So in civil engineering, we are going to discuss this procedure for four practical cases, which are pedestrian-induced vibrations of footbridges, vibrations of high-rise buildings, machinery-induced vibrations in buildings, and vibration caused by traffic. In mechanical engineering, there are 5 case studies. The first one is payload comfort in space launchers. The second one is engine vibration. The third one is car suspension for passenger comfort. The fourth one is aircraft tail or wing vibration. And the last one is fatigue in wind turbines. Well, it seems that we have set the background. In the next videos, we will go into more theoretical and applied considerations.